Okay, YouTube, thanks for tuning in to my channel. Today I'd like to take probably just a few minutes here and give you a sense of um, artificial gravity and in real terms, like what it actually looks like in scale. What does it take to achieve 1 g of gravity? And these are some models that I made right here on the screen. Of course, not all of the models are things that I made. I didn't make this. This is for scale representation, the Eiffel Tower. But otherwise, these are models that I've built to kind of demonstrate and illustrate to you the size and scale of rotating gravity in space. So if you've ever seen pictures or been to the Eiffel Tower, this will give you a sense of scale compared to these other objects. So let's go ahead and get started. I have a lot of other objects to cover, okay? So this first one right here represents a rotating habitat that's constructed with basically either two starships that are put together or two other well, these are 9 millimeter diameter capsules. So they could be starships or some other kind of construct, but it gives you a sense. So if we zoom in here, this object right here is a human scale. It's roughly 2 meters of height. Okay, so as you see this habitat coming around, it shows you like how tall you are, and of course you'd be standing on the inside, feet towards the outside, and then head towards the inside, so that you can utilize the spin gravity. So with this scale that we're looking at right here, this is designed to give you 1 g of gravity in a period that's a quarter of a minute. So every 15 seconds, this will spin around and do a 360-degree spin. So radius 56 meters. You can zero in or pause to get all of these specific measurements if you like to. I'm just going to go ahead and go on to the next one. All right, so this is another one. I think it kind of illustrates just how fast you have to go, and this is not even 1 g. This is 0.4 of a g, and look how quickly you have to spin around. So naturally, this is too quick of a spin to actually be in it for a long time without getting sick. This one right here is just slightly bigger. By the way, if you look at how I created this, so basically these long flat planes start here at the center axis, and that's basically represents the circumference. So it shows you how much living space. So here's a person, and this is how much living space that they would see on the inside, of course, but it's curved. Okay, so for that one deck. Okay, so this other one, I have to expand out, and then it's at a different scale, the text. So this is 1/3 g, rotates five times per minute, and here's all the specs for it. Now we're going to continue scaling up, because you'll see quickly what it takes to actually get a comfortable spin gravity. Okay. Again, here's a person. Here's the habitat. You can see how fast it's spinning, and you can see how large that living space is on the inside. It's actually quite a lot of square footage if you look at that one person. So this is a 50 meter radius. 3 rotations a minute is giving you only a half of a g. Okay. which is still more than it's still a lot more than Mars, which is 1/3 G. So, well, Mars is roughly 1/3 of a G. Um, so this is 1/2 G. This one will be 3/4 of 1 G with a 75-meter radius. Circumference 471 meters. So that tells you that this plane right here is 470 something meters from end to end. And that gives you quite a bit of living space. But now, keep in mind, you're still only at 3/4 of a G. So let's go up to the next one. Oh. Yeah, I believe this one, yeah, this should be 1G. This should be my first one that's 1G. I stopped I stopped putting in that little box to represent a person, because it just you're getting so big at this point. But you can still see how quickly this is rotating. All right. So that's a 100-meter radius. It rotates 3 times a minute. And that gives you 1.006 G. So basically it's a 1G environment. Okay, so this one here is based on Calpano 1, which is a design that's been popularized online. Brian Versteeg is one of the people who are involved with it. He's one of my favorite space artists, to be honest with you. And so here it is compared with the Eiffel Tower. Okay, you can see it is quite a bit bigger than the Eiffel Tower at this point. There's an enormous amount of space inside. And then this is starting to get to the point where it spins slow enough so you're not feeling the effects too drastically. And so that's also roughly 1G with a 500-meter diameter and a 250-meter radius. Okay. And so here I started kind of playing around with things a little bit. This construct is much, much bigger. This is what I would consider a good size for a city in space. This is this is the one that's for, ooh, go back to that. Ah, man, it's kind of hard to control things in this scale in Blender. Okay, so this is one that's a city for 10 million people that I've been playing around with the idea. So this one has 10 different decks. So these decks would be collapsed and then curved into a cylinder space. So those decks would basically be around this edge right here. Okay, and that gives you the size of the Eiffel Tower. Quite big, but still the cylinder is huge, and 1 rotation per minute, which is actually really comfortable according to scientists who have reported on these, have researched these things. With a radius of 890 meters, diameter, what's the circumference? 5,600 meters. Okay, 5.6 kilometers. So from there, that's really, really large as far as practical space colonies in the next few hundred years. If you start scaling up, oh man, it really is hard to see things in this scale. But here's some other examples that are much, much bigger. Radius of 8 kilometers, circumference 50,000 kilometers. I'm sorry, 50 kilometers. What am I talking about? It's a circumference of 50 kilometers, has a spin rate of once every 3 minutes. Here's once every 4 minutes. Blender does not seem to like me for having such large objects. I've UV unwrapped these objects and they're still giving me issues. Control A. Yeah, and you can see that this has been UV unwrapped, and it has the same materials as everything else, but it does not want to play along with rendering properly on the screen. And so this one here, oh gosh, the biggest one has a rotation speed of once every 10 minutes. But I don't even have my other information about that one. So that's it's very large, obviously. It's clearly a extremely large object. Personally, I'm a little bit more enthusiastic about smaller ones like this one, which I would consider to be like a city size. You know, you could have this is more like an O'Neill cylinder. If you had two of these connected, somehow they would, you know, their spinning would counteract each other so that they wouldn't go out of control. You'd have to have two of them connected to each other to achieve that without having them go out of control. Otherwise, they're going to spin in really weird ways. Even if you started the spin in a nice, you know, round spin, it would just start going out of control unless you have two of these connected. And I'll have to, let's see, on the X. So if you had two of these connected like so, and then they were connected from here to here on each side, and then this one would have to rotate the opposite direction. -1. No, I can't get it to rotate the opposite direction. Scale on the Y. Nope, still spins the wrong direction. But I could play with it and get it to spin the opposite direction. Okay. So that ends the video. That's just my my basics analysis, a demonstration to show you what the scale of things and what the spin rates look like in real time. And if you do have any questions, please leave a comment below, and I'll be happy to take a look at it and offer any suggestions I can. Thank you very much.